value, it's 7FFF. But when truncated by 4 bits, this number suddenly becomes negative. So if one component of the software uses 16-bit and there's a test, is the value larger than 0? And the answer is yes. And you put this value into a smaller register or a smaller bit field, it suddenly can become negative and you can access memory perhaps somewhere else. This is why integer overflows are evil. Okay. Here we found something on PowerPC 64. We found a 32-bit integer overflow when accessing data segments. Data segments are created to store constant data, and it's a 64-bit address machine, so the data segment could possibly be 64-bit wide. And the problem is, in the marked lines, the displacement is cast to a short, which is just a 32-bit value. So instead of accessing memory at a positive offset, it could be accessed at a negative offset because we cut off a few bits. Nonetheless, this bug is not exploitable because there are no data segments this large. Java class files always have limited size. They have a limited numbers of constants, limited numbers of methods, and 4 gigabit is just too big. It does not fit. But we found more. On AMD 64, we found another 32-bit integer overflow. This time, the argument of a conditional branch, which gets generated by the function emit GCC. And in the last line, you see the argument or the branching offset, it's just a 32-bit value. But it is, again, a 64-bit machine, so here a truncation happens and we again have an integer overflow. But that again, it is not exploitable because no method is larger than 2 gigabyte of instructions because in class file they are much smaller already. On PowerPC 64, we then found a 25-bit integer overflow, and this is very close to be exploitable, but just not. Very bad. Again, it's conditional branching. And on PowerPC 64, there are 32-bit fixed-size instructions. And when branching with a condition, a lot of bits get used just for this is a branch, this is the condition, these are the arguments, and there are some bits left for how far to jump. And when generating the conditional instruction, the displacement gets truncated, but again, it's always inside the range of a method, and so it cannot be exploited. But on PowerPC 32, we had luck. We found a 16-bit integer overflow. And this is about a virtual table of an object. In the virtual table, my friend Peter will explain this in more detail. There are all the method indexes, and we can overflow it. And we will overflow it, be negative, come back again, and so trick the bytecode verifier into executing stuff. It thinks it is secure. We implement a very nice feature with that bug. And we also found a bug on what we call medium level serosity. This is a bug with exception handling in Java. When you think of Java exception handling, you always think of the try catch block, and you cannot enter the catch block without an exception. That's not possible. It's only entered when the exception occurs. And you catch this exception, and you have this exception object, E. It's a variable for this block, and it's always there. And you can only enter this block with an exception. That is true in Java, but it is not true in Java bytecode. And this is what gets executed, finally. In Java bytecode, you can have something like a false through in the C switch statement, where you can false through the labels as well. And you can do that in Java bytecode. And whoever wrote the exception handling code in Kakao was not aware of this or did not think of this nasty detail when initially writing the code, because he thought of Java, but he should have thought of Java bytecode. But no one is really that familiar with that, and so this seems to have happened. And by chance it happens that Kakao, this exception object, which is the argument for the catch block, by chance is an integer register. And by some good arithmetics, we can control the contents of that integer register, then fall through and have fun again. Okay, and now Peter will show you the exploits, and yeah, thanks.
So to actually implement exploits for these vulnerabilities that we have found, we're going to implement fake Java objects from within Java code, populate their methods with arbitrary code that will be our shell code, and then pass control to the shell code by executing one of those methods. So let's have first a look at how objects are represented in Kakao. Any reference type, any Java reference type like object or string is just a plain pointer to an object that is located on the heap, and such an object consists always of an object header followed by all instance fields. If you now call a method in Java, like toString, the code that will be invoked is not determined at compile time, but rather at runtime. And the selection of the codes works as follows. If you have the object pointer and invoke, say, object toString, first the virtual function table pointer is loaded from offset 0 of the object pointer. Then the name of the method is converted to a method index, and this index is used to load the entry point of the method from this virtual function table. And finally, this, the executable code is called. Java arrays are Java objects too, so they contain an object header. Then this object header is followed by the number of elements in the array. This is collectively called an array header, and the array header is followed by the array elements. We want now to construct such a data structure from within Java code, and we can use arrays to construct such a thing. We can use a byte array to put some executable machine code into the byte array. We can use an array of integers of the native word size to create such a virtual function table, and we can use such an integer array to create this object header. But we still need to set up the pointers correctly in the data structure, so we need two things. One, given if we have a Java array, we need to retrieve the address of the first element of this array to set up those pointers. And to pass control to our code, we need to convert some arbitrary address to a Java reference type, like say object. To solve both these tasks, in our first exploit, we're going to use the 16-bit integer overflow that Roland has presented. And this overflow happens under some circumstances where the entry point is loaded from the virtual function table. The offsets into this virtual function table are in fact 18-bit wide. But in some situations, the offset is just truncated to 16 bits. So let's have a look at what happens with this offset after truncation. So let's now suppose that the offset is not truncated to 16 bits, but just to 4 bits. So we have here such a table. In the left column, there is just a sequence of increasing offsets. And in the next column, we truncate this offset to a 4-bit signed value. So we see that for some offsets, they will keep the same value. Then for some other offsets, they will become negative. And then for the next set of offsets, they will become positive, but have some different value that was intended. And these offsets are then used as indices into this V table. So if we want to address the first group of methods, they will be addressed correctly. Then if we want to address another set of methods, the index will become negative, and instead of loading the entry point of the method, some garbage pointer from before the virtual function table will be loaded. And for the next group of methods, the entry point of some different method will be loaded instead of the real entry point. At this point, we have a misbehavior where if we call a method, some different code will be executed, and we can use this misbehavior to implement interesting stuff. We write such a big class, it's called big, and it contains some 16,000 trivial methods that all just take an integer argument and return this argument as return value. And we add two more methods, one int to object and one object to int, that both take some argument and just return some dummy value. If we now call this int to object, because of this integer overflow things, one of those 16,000 methods will be called instead, and because of the calling conventions where addresses and integers are passed and returned in the same registers, the argument will be just reinterpreted into some different type and just returned. So using such a class, we have implemented an interesting feature, an unsaved C-style cast for Java, and the type system and type safety is bypassed at this point. So having these two cool casting functions, we can go on and construct our fake objects. So we create an instance of this big class, we create our shellcode that can be arbitrary machine code in a byte array. We create this virtual function table with enough entries for enough methods as a integer array. Then we use our object to int function to get the address of this byte array to populate the virtual function table slots, but we need to always add a fixed size constant, which is the offset of element 0, because we have this array header thing before element 0. Using again object to end, we set up this object header in a integer array. At this point, our fake object is complete, and we use now this int to object thing to convert the address of the fake object header into a Java reference type, a object. And finally, by invoking some virtual method on this reference type, we pass control to our shellcode. I'm going to demonstrate this now. Okay, so we have implemented this and compiled already. I'm not going to compile it again because the compilation of this huge class just takes too much time. Let's see what Kakao we have installed here. Okay, it's It's 0.97. It's, I think, some previous release, but it's just the default Debian package installed on the system. So I'm going to invoke the thing, and we just have an operating system shell. This may not look like an interesting thing because you can just fork off a shell from within Java code. But the idea is that if you use this in